All right, good morning, students. As you have seen when you walked into class today, the desks are not in their ordinary position because there is a test coming up for the whole grade level. And instead of changing the seats back and then changing them back again at the end of the day, I'm just making this video to where y'all can still get the lesson and I don't have to move these desks. Honestly, that's the true reason behind this. So let's begin, shall we? You should have got a packet that says second verse, same as the first, and it should have a number 3 on it. If you are in first, second, or fifth period, yours should say 625. If you're in my third period, it should say 711. And if you want the Spanish version, it is on slide 19, and it is numbered along with the pages I'm going to go over right now. If you are using Class Kick and you are following along the Spanish version, I would suggest you open up a second tab just because you have to watch this while going through the lesson. So to make it easier to switch back and forth, open up another tab and that should solve the issue. So let's begin. This is talking about equivalent expressions and it requires you to do certain things. First up is the homework. There are 3 parts to the homework because it's in 3 different parts of this packet. So the first one is some simple solving problems in the front. This is going to be part of the homework. This homework you will be turning into Schoology. Okay. We will be skipping this page. All right, turn your packets to page 627 or 713, depending on what class period you are. And we're going to be starting in activity 3.1, algebra tiles and combining like terms. So as you've seen in the previous activity, when using algebra tiles to model situations or expressions, it's important to have a shared meaning for each differently sized algebra tile. Your teacher will hold up each differently sized algebra tile and tell you the conventional value of each. So right now I'm just going to find those tiles because I did get some so you can see what they look like. At one point in this packet, you will be drawing them. So give me one moment. All right, I paused the video for a moment, but now I'm back. So I have the algebra tiles. Now the color doesn't really matter, but what they represent matters. So the first one we have is this one. As you can see, it's a small little square. On one side is negative, one side is positive. This just counts as a 1. So this is what you would use for your whole numbers. So we're going to sketch that right here. And it counts as a 1 tile. Whether it's positive or negative depends on your number, but it's a 1 tile. The next tile is this tile. As you can see, one side is negative, one side is positive. This long triangle is for our very first variable. The reason it's so long is because we don't know how big the number is until we solve for the variable that it is. So this represents x, and once again, x can be negative or positive. There's a last one that's going to be used throughout this lesson, and that's this big old thing right here. So it also has a positive and negative side. The color is not what matters, but what it represents. This is a 2x. So x to the power of 2 or x squared if you want to get use the special name. So that's what should be written on your paper so far. Let's continue. Represent each numeric or algebraic expression using algebra tiles. Write an addition expression that highlights the different tiles used in the model. Then sketch the model below. So this one would be 1 plus 1 plus 1, and it would look like that. This one, x plus x plus x. So that means we have this plus this. Kind of making it shorter because I do have another one I have to do, because we still have to do this one, plus this. So this is what it looks like written out. This is what it looks like with the tiles I showed you a moment ago. And then last but not least, 3x squared, or 3x to the power of 2. So that's x squared plus x squared plus x squared. Remember, the number in front of the variable is the coefficient, and it tells you how many of the variable we have. That includes the exponent, because the exponent is touching the variable. So that's 2x plus 2x plus 2x. So this is what it looks like to represent each one of these. Remember, any number that doesn't have a variable is called a constant. The number with the variable is called the coefficient. And then, of course, you need to remember how to say your exponents. To the power of, raised to the power of, or if it's one of the special ones, squared for 2 and cubed for 3. All right, let's continue, shall we? So it says, in an algebraic expression, like terms are 2 or more terms that have the same variable raised to the same power. So if you think about the example we just done, that's like terms. So if it's a constant, which means it's a number that does not have a variable, if you have more than one of those, you have like terms. So this whole lesson is getting you to understand like terms, because you can only combine things that are alike. So let's continue. Given the algebra tile model, write an addition expression that highlights the different tiles in the model. Then, if necessary, combine like terms and write the expression using as few terms as possible. So let's look at what we have here first. We have these tiles, then these, then these. Excuse me. So first they want us to write an addition problem, kind of like the one we just did on the previous one. So we have x squared plus x squared, because we have 2 of those, plus x plus x plus x, because we got 3 of those, plus 1 plus 1 plus 1 plus 1, because we have 4 of these. Now, they said combine like terms if possible. Well, I see that these two are x squared. And since x squared is like x squared, I can combine these and do 2x squared. These are all x's to the first power because they don't have an exponent. So they are just x to the first power. So we have 1, 2, 3 of these. These are like terms because all of them are a variable. The coefficients do not have to be the same when you are combining like terms, but if it has a letter, they have to have the same letter. And if they have a letter and an exponent, the letter and exponent must match. So this would be plus 3x. All of these don't have variables, and like I said, a number without a variable is called a constant. So we can combine these together for that simple fact. They are all constants. So that would be plus 4. So instead of writing all of this, we can simply write this and it means the same thing. That's combining like terms. They have to have the same variable, or if they have an exponent, the variable and the exponent must match. And of course, if it's a constant, it shouldn't have a variable at all if it's to be combined with other constants. Now it says, how many terms are in your expression with the fewest terms? Well, if you look, we only have 1, 2x squared, 3x, which makes 2, and then we have 4, which makes 3. So the short expression has 3 terms. And then it asks, how does this relate to the algebra tile model? Well, how many different tiles did we use? We used an x squared, so that's one kind of tile. We used an x tile, so that makes 2 types of tiles. And we used a number tile, which makes 3 types of tiles. The model used 3 different tiles. Now, did it use more than 3 tiles? Yes, but we only had 3 different versions of those tiles, which is what it's saying. What is the greatest exponent in the expression? Well, we only had one that actually had an exponent. The greatest exponent is 2. Now, if you couldn't see that, go back and look at the example. What is the coefficient of x in the expression? How does this relate to your algebra tiles? Now, it's not asking about x squared, it's simply asking about x, these tiles. So the coefficient of x is 3. How does this relate to the algebra tiles? There were 3 x algebra tiles used. Because remember, we are no longer writing one-word answers. We are writing sentences to explain ourselves and what we mean in these situations. All right. Let's go ahead to the next one. On this page, let me catch up with myself. We're doing 2 problems. So it says consider the model. So we have this, 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 and this. So it says write an addition problem to highlight the different tiles in the model. So unlike the first one where I wrote out every single individual one, we're going to write these into the clusters that we see them in. So for this first one, we see 2x tiles. So we're going to put 2x. Here we see plus x squared. Plus, here we have 1, 2, 3, 3x tiles. So that's 3x. Plus, we have 2x squared tiles. So 2x squared. So that is the combination of tiles that is being used in this problem. It says rearrange the tiles to combine all of the like tiles. How many terms does your expression have now? Well, if we combine it, I usually like doing this from the highest exponent tiles, putting those first and then putting it in order from highest to lowest. So what I'm going to do is I'm going to move this in front because it has the highest exponent, plus this one, which has the highest exponent, that's the same as this one, plus this, plus this. Now, since this is addition, I am allowed to move these things where I need them to go. Notice that these all are x squared. Remember, like terms is having the same variable and exponent value. Both of these have an x variable and a power of 2. These two are like terms because they both have a variable with no exponent, which means the exponent is 1. But how many terms do they make together? Well, since I'm going to combine these two, there are only 2 terms. And what does that look like? Well, this is 3x squared, because I can combine these two, plus this, which is 5x, because I can combine these two. And this is what my expression will look like simplified. So this is where I tell you that if it tells you to evaluate an expression, if you don't know the value of a number or you don't know the value of this letter, you can simply make the expression simplified. You can make it shorter. We're skipping number 6. Okay, we're skipping number 6. We're not doing that. So it says algebra tiles are helpful tools for combining like terms in algebraic expressions. However, so there is an instance where you're not going to be able to use an algebra tile. Because they only represent whole number tiles, they cannot be used to model all algebraic expressions. So that means if you needed to do something like these, which are decimals and fractions, you're not going to be able to use algebra tiles because algebra tiles only use whole numbers. So we're going to have to figure out a way to write these. Now, this is a good place to start using the highlighter, which is another reason I like Class Kick. So we're going to be using the highlighter to highlight the terms that are alike. And that's the first thing we're going to do to all of these problems. If you don't have a highlighter, then I would suggest you do use your pencil, but use like different shapes. For X, you can use a square. For X squared, you can use a circle. For constants, you can use a triangle. You can use these different symbols if you don't have a highlighter, just to notate the different things you're doing. So for me, the circle will be for the constants. So these are the numbers that don't have variables. I will also be using a highlighter afterwards so that you can tell the difference. The triangles will be for, matter of fact, I don't have x squared. So since that's the case, we're going to use the square for a single variable with no exponent. I don't want to write too far in here because this is where I'm going to be putting my answers. So let's look at this first one. We have 2x plus 3x minus 4.5x. All of these have a variable x of 1. So all of these are like terms. So I will be solving, simplifying this one because I still don't know what x is. B, we have 3 1/2 x plus 2 plus 4x plus 1 1/4. Okay, well, these have a variable of exponent 1. These don't have a variable, so these are my constants. All right, C, 4.5x plus 6x minus 3.5x plus 7. Okay. All of my single variables, so all the ones to the power of 1, we want to combine those. We will be dealing with these operations in a moment. And then this is my only constant of the bunch. D, 3/4 x plus 2 plus 3/8 x. So we have our single variable. And then we have one little constant here. All right, for E, we have 5x plus 2x plus 1/3 x squared. Oh, we do have x squared. So that's going to be a variable. To the second power. X squared minus 3x. So I have single variable. And then I have x squared. So in highlighting terms, we have this, 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 this. Remember on your STAR test, since it is online, you will be able to use a highlighter. You'll also, if you ask for it, usually it's given to you. There will be I don't like that color. There will be highlighters given to you when you are taking STAR. If you want to write these type of problems down and highlight the like terms yourself, then do that. We'll go with this one. Nah, that's too close to that. Let's do it green. So as you can see, I have 3 different colors. I have these all representing my single variables. Then I have these colors representing my constants. And then I have this color representing my variable squared. So to the very next power. But we still have to solve these. So let's begin, shall we? So now you have to take into consideration the operations that's happening now that we know what our like terms look like. So let's look at A. And if I look down, that means I'm looking at my paper because I'm going to be scrolling down and then putting my answers back here. So here we have 2x plus 3x. So 2 plus 3 is 5. So we have 5x minus 4.5x. Now remember, anytime we see subtraction now, you are to do KCO. And I'm having you practice the skill because if you practice it now, it will help you later on. So that gives me 5x plus negative 4.5x. So when I subtract this, since we have different signs, we're going to be subtracting, number 1. Number 2, when you are subtracting with decimals, you have to line them up by place value. So this is a ones digit, this is ones, and this is 10th. So we have 5, 4.5. Since I do need to have a number over here, I got to put a point and a 0 and take it from there. So I cannot take 5 from a 0, so borrow. That gives me 5, and then that gives me 0. And then since we are subtracting, and this only works with subtraction and addition, we bring down the decimal point. So that gives me 0.5x. For A. Now let's look at B. We actually have 2 different things. I'm going to start with the variable because that's what I'm going to write first. But you can also start with the whole numbers. It really doesn't matter. since we have to reorganize this to solve it anyway. And all we're doing is combining like terms. So we have 3/1/2 x plus 4x. Now, when adding mixed numbers and whole numbers, it's fairly easy because you can simply add the whole numbers. So this is 3 plus 4, which is 7. And then there's no fraction for this one. So we just keep what we had before, which is the 1/2. So that makes that's 7/1/2 x. Same for whole numbers. We have 2 plus 1/4. Combine the whole numbers together and then combine the fractions. This is 2 plus 1, which is 3. And then there is no other fraction besides the 1/4, so put it at the end, and we get 3/1/4. So this one is 7/1/2 x plus 3/1/4. For the next one, the only thing we're combining are the x's because we only have one variable. One constant, which is 7. So that's going at the end. So we just got to figure out what this is, and then we can rewrite it. I actually don't have space to rewrite this one, so the answer will just be down here. So we have 4.5x plus 6x minus 3.5x. Okay, so for this one, we're simply adding. Remember, when you're adding with a decimal, you have to line them up by place value. So that means the 6 is going to be over the 4. So that gives me 10.5 because this one doesn't have a decimal point. So the decimal place is not changing. Minus 3.5x. Remember, since I have subtraction, I do KCO. So that gives me 10.5x plus negative 3.5. So I am subtracting these two, and then whatever I get is the answer to my sign. So I'm going to line them up. That gives me 0. 10 minus 3 gives me 7. So this is 7x plus 7. And remember, I told you I can't write it up there, so I'm going to leave it right here. So this is 7x plus 7 for C. All right, moving right along to D. D, once again, we only have one constant, so that's going to be at the end. So I have to combine these two. Now, the thing about adding fractions together, you cannot add fractions if the denominators are not alike. This is where the greatest common multiple comes into, the least common multiple, LCM, the least common multiple comes into effect. So when looking at my denominators, they have to be the same. So right now I have a 4 and I have an 8. Excuse me. If I were looking at the answers to a multiplication problem, what would they equal that is the same? Well, both of them can equal 8 because I can do 8 times 1 and I can do 4 times 2. So I'm going to increase this one by 2. And I'm going to increase this one also by 2. So this gives me 6/8 x plus 3 8 x. So now that my denominators are the same, my denominator stays the same, and my numerator is 6 plus 3, which is 9. So that is 9/8 x. Now, I left this as an improper fraction because there was no need for me to turn it into a mixed number, but remember to pay attention to your answer choices and what they're looking for. So this is 9 8x plus 2. All right, so last but not least is e. Okay, for e, we only have 1. That's to the power 2. I told you I like to write mine in the procession of the variable with the highest exponent. So this is 1/3 x squared because there's only one of those. And then I have to figure out what this is. So we have 5x plus 2 minus 3. So that gives me 7x minus 3x. I perform my KCO. 7x plus negative 3x. And that gives me 4x. So this is plus 4x. If it was a negative, it would be minus 4x, but it's not. All right, at this point, if you have any questions that you would like me to answer, please just raise your hand as I will be walking around the classroom to be checking for your work. On to the next page. We are now on page 630 or page 716 if you are in third period. So the only important thing I wanted you to take from this page is when you are speaking about algebraic expressions that is grouped together with parentheses, use the words the quantity. For example, we have 2 times x plus 3. In words would be 2 times the quantity x plus 3. So the quantity is, when you say the quantity, that's to let us know that there are parentheses back, forward, and back coming up next that encapsulates these. So quantity. So instead of saying beginning parentheses and then saying what's inside, then ending parentheses, just say quantity, the quantity, and we'll know that there's parentheses there. All right, here's an example of how algebra tiles work, because that's what the next part is going to be about. Turn to page 631 or 717, depending on your class period. We are not doing this. We're not doing that. We're doing this one. So it says create a model of each expression using algebra tiles, then sketch the model and rewrite the expression using the distributive property. Remember, the algebra tiles were this small square for the constants, so the regular numbers with no variable. You had the long rectangle, and it doesn't have to be that long, but it does have to be a rectangle for your x variables. And then you had the bigger square for your x squared. Now, this is how algebra tiles work for these situations. You have the part in the parentheses and you have the part outside the parentheses. And since it is that way, this is how you have to set it up. So you basically draw like a version of a multiplication table. This means you are multiplying this with this. So the number on the outside, I'm going to put that here. And then whatever's inside the parentheses, I'm going to put that here. Does it really matter? No, the process is the same. It's just for me, in the order I like to see it in, that's just what I'm going to do, even for this one. So we have 4 on the outside. So I need 4 of these small squares. So remember, this for me represents the number outside the parentheses. And you have to do this one distributive property at a time. Then I need this stuff inside the parentheses. So that's 2 x's, and a 1. And then you solve this like you would a multiplication table. We have 1 times x, that gives us 1x. 1 times x, 1x. 1 times x, 1x. 1 times x, 1x. All right, so I finished that column. Next, 1 times x, 1x. 1 times x, 1 times x, 1 times x. Finish with column 2. Last column. 1 times 1, 1 times 1, 1 times 1, 1 times 1. So when we are done, we have 1, 2, 3, 4, 5, 6, 7, 8 x's, and we have 1, 2, 3, 4. 1 squares. All right, now let's try B. I'm going to help you set it up, but as for solving it, you're going to do that on your own. So we have this. Remember, we're setting up a mini multiplication table. My number on the outside is what I'm going to put here. So that's 2. Here, I'm going to put what's in my parentheses. So that's 3x and a 1. All right, pause the video and solve this yourself. I will be walking around if you have any questions or need any help solving this. This is just to deepen your understanding of how algebra tiles work. All right, hopefully you're done solving B, as you should have paused the video so that you can get done. All right, moving on. Page 232, page 718, depending on what class period you're in. So it says rewrite each expression using the distributive property, then combine like terms if possible. This video is already 38 minutes, so as much as I would like to solve all of these, I will only be solving a couple of them just so you can get the gist. As I'm looking at the page now, that's going to be A, B, and C. The rest of them you would have to solve on your own from the examples that I'm doing. So distributive property, it says I can also use distributive property like this, and it gives you an example. So if you want to, you can draw that algebra tile table that you just did on the previous page to solve all of these, except for the fraction one. Let me rephrase that. Except for the fraction ones, because the algebra tiles only work on whole numbers, not fractions. So you won't be able to do it for B or F, but you could do it for all the other ones. So looking at this, excuse me, remember, the distributive property means to give. So we are giving something through multiplication. So that's the number on the outside. So I'm giving this 2 through multiplication. So this is equal to 2 times x plus, because we keep the operation, 2 times 4, which is equal to 2x plus 8. For this one, we are distributing or giving the 2/3 through multiplication. So that gives us 2 thirds times 6x plus 2 thirds times 12. Now remember, we cannot do fractions and whole numbers, so I'm going to turn this one into a fraction. That gives me 2 times 6, which is 12. 3 times 1, which is 3. X. 12 over 3 equals 4. And I keep the variable, so it's still an x. Here, I'm going to turn this into a fraction. So that's 2 times 12, which is 24. 3 times 1, which is 3. 24 over 3, or 24 divided by 3, is 8. So plus 8. The last one I'm going to show you is this one. You can only do one distributive property at a time. Okay? So, let's begin. We're going to start from left to right. We're going to get through this with multiplication. So that's 2 times x plus 2 times 5 which gives us 2x times 10 plus 4 times the quantity of x plus 7. Then I got to distribute this one with multiplication. So we have 4 times x plus 4 times 7. So that gives me 2x plus 10 plus 4x plus 28. And while you think I'm done, remember we are supposed to combine like terms to simplify these as small as possible. So I have an x to the exponent of 1, an x to the exponent of 1, and I have a constant and a constant. So 2x plus 4 gives me 6x, and then 10 plus 28 gives me 38. And that is it for that. Like I said, the rest of this you would have to solve on your own because we don't have any more time. Ooh, but I still got quite a bit to do. All right. To hurry this on. Page 633, page 719, depending on what class period you're in. The distributive property also works with division. So this is the first instance of this. So if we can distribute by multiplying, we can also distribute by dividing. The only thing is, just like you have to multiply with everything inside the parentheses, you also have to divide everything inside the parentheses if you're doing its opposite operation. So here we have 4x plus 8 divided by 4. Well, I already know I'm going to need 4 groups. So I'm going to put lines. So this is 1, 2, 3, 4. I need to split this into 4s. Well, looking at this one, we have 4x. So if I'm splitting it into 4s, that means I'm going to have 1x each. I'm actually doing A and B together. That way I don't have to draw this multiple times. So that's an X each, and I have split all my X's into those 4 groups. Next is the 8. So how much am I going to have per group if I have to have 4 groups of this? Well, 1, 2, 3, 4, 5, 6, 7, 8. Looks like I'm going to have 2 each. Now, like I said, I did A and B together because I drew the algebra tiles and then I split them into groups. Give me one moment. All right, I'm back. So I did A and B together. So scrolling down, write an expression that represents each group from your sketch part in, I know this says B, but it's going to be in A.
Good morning, teachers.
This is going to be part A, so that would be X plus 2. Now it says to verify that this is correct, we're going to multiply. So remember, we divided up top. To check our answers, we're going to multiply this by 4. So if I distribute, remember distribute means to give through multiplication, we have 4 times X plus 4 times 2, which gives us 4x plus 8. So this was distributed correctly. All right. So if this is the end part of class, then just finish this later because I am going to continue the video because there are other parts of the packet that I want to go over. And there are skills that you need to practice, and I want to make sure you're able to do your homework. So on the next page, page 634 or 720, it shows you an example of the division problem by splitting it up. So that's another way you could do it. We're not, I'm going to do the algebra tiles real quickly. So we have 2x to the power of 2 plus 6x plus 4 divided by 2. So we need 2 groups, and I'm going to be splitting this as I go. So this twice, since I have only 2 of them, that means I need 1 in each group. Six, I'm going to have to split into 2 groups. And then the 4, I'm going to have to split into 2 groups. Okay, they lied when they said this lesson was 45 minutes. All right, so everything has been split and divided by the 2. Because remember, we have to divide everything by the 2 since we are dividing, we're giving the 2 to everything through distributive property. So it wants us to rewrite this. So, of course, all these boxes have 2 in them because we have to divide everything by 2. So that gives us x to the power of 2, or x squared, plus 3x plus 2. And that's exactly what we got in our model. And if we take in considerations all of this, 2 divided by 2 is 1, 6 divided by 2 is 3, and 4 divided by 2 is 2. So that is how it works with division. We are actually going to be skipping the next page. I'm not going to do it at all. Okay, this is going to be the last activity, even though there is an activity 3.4. I would suggest you use 3.4 as practice at home so that you understand the concept better. But the last thing that is related to distributed property is factoring algebraic expressions. So it says you have used the distributed property to multiply and divide algebraic expressions by a given rule. The distributed property can also be used to rewrite an algebraic expression as a product of two factors, a constant and a sum of terms. So what this means is, remember I told you many things in math have opposites. Well, the distributive property has an opposite too. It's called factoring. It's where you work in reverse. So if you can't simplify by going forward, you can simplify by going backwards. So here's how it works. Well, this is one way it works, but you can also use the greatest common factor to figure out how to do this too. So I'm going to show you both ways. So it says identify the coefficient of the variable term. So the coefficient, well, I'm not going to show you with this one because the coefficient and the greatest common factor are the same thing. The coefficient is 3. Okay. Remember, the coefficient is the number with the variable, and the coefficient is 3. Use the distributive property to rewrite the expression as a product of two factors, a coefficient and a sum of terms. So that means we're going to do 3, which is the coefficient, and inside is the sum of terms. So the way to do this is you are basically practicing division. So we have 3 divided by 3, so that gives us 1, so that 1x. And then we have 6 divided by 3, so this is plus 2. So that's our coefficient and a sum of the terms. Now check your work. So what they want us to do is to see if we are correct, use the distributive property to see if we get back to our answer from before. So that gives us 3 times x plus 3 times 2, which gives us 3x plus 6, which means we are good. Okay? All right, and on to the final page that I'm going to talk about. This just explains what we just did, so if you want to read it yourself. Here's an example of what we were doing, because like I said, factoring requires you to do division, which is the other side of the distributive property. If you can multiply it, you can divide it. So it says write each expression as the product of two factors. Check your answers. So honestly, I'm going to go through this real quickly, but if you don't understand, I suggest just play the video slower. So the coefficient in this one, there is another way to do this, but none of these numbers work to my advantage. So we're just going to keep practicing the same strategy. But once again, if you don't want to have fractions and you're able to, then find the greatest common factor if they have one in common and do that instead. So for this one, we have 4 as our factor. We're going to divide both of these by 4 since we're taking the coefficient of 4. So that gives me x plus 5 over 4. This one, the coefficient is 8. So I'm going to divide both of these by 8. That means my 8 is here. 8 divided by 8 is x minus 3 over 8. And that is my product of two factors. Here we have a half. Remember, you can't show fractions with algebra tiles, so none of these, or decimals, so none of these will work with the algebra tiles. So our coefficient is a half. So I'm going to put it right there. Now, in the case of the half, in the case of a fraction, you can divide by a fraction, but it would be better if you multiply by its reciprocal, because the whole goal of this is to get the x to equal a 1. So I'm going to multiply by the reciprocal. How I know this works: 2 times 1 is 2, 1 times 2 is 2, and 2 over 2 equals 1. So that's 1x, which is exactly what I was trying to do. This is why you multiply by the reciprocal, to get the x value to equal 1. And usually a positive 1 at that, but we'll get into that later. This is 4 times 2 over 1. 2 over 1 is equal to 2, so 4 times 2 is 8, and that's for that. Then we have 1.1x plus 1.21. So my coefficient is 1.1. And then I need everything inside, so divide. So 1.1 divided by 1.1 gives me 1x. And 1.21 divided by 1.1 gives me 1.1. If you were wondering how I was able to do that so quickly, 11 times 11 is 121. And since this has 2 decimal places, both of these must have 1 decimal place each. All right, that is it for the lesson, although that's not all I wanted to talk about. But next time I'm going to have to reduce this a bit so that we can get through everything. So page 638 and 39, also page 724 and 25 are problems that you can work through on your own. I wanted to go over these, but we didn't have time. I might go over them during a lunch tutorial or make a separate video just in case you wanted to get a little help setting these up. I'm not going to help you solve them, but I will help you set them up. Same thing with this page. This is just extra problems to solve. As you can see, they can get quite long. And this is the introduction to algebra, so they will be getting longer. Last but not least is this page, which is homework. So what you are doing is they give you an expression and then tell you ask you which ones are equivalent. If it is equivalent, you're going to turn this into Schoology. If it is equivalent, you're just going to put equivalent. If it's not equivalent, you're going to have to explain why it is not equivalent in a separate section of the homework for both of these. There is also nothing here. There are also these 2 problems here, which are also going to be in the homework. This one says determine which rate is faster. So you have to determine which one is literally faster. So you have to determine that in some kind of way for both of these. And then these are practicing volume, which we haven't went over in a while. But this will be a nice review to see if you still remember how to find volume. And you're finding volume of multiple figures, because these are composite figures. So they are 3-dimensional shapes that have been put together. Although I will kind of tell you they are very similar. Matter of fact, this one is the same thing 3 times. So you should be able to figure that out. And if not, I would suggest you ask in a tutorial class. All right, class, that is it. I hope this video helps you understand how to find equivalent expressions. And I look forward to seeing what you can do. Bye.